Hi, everyone. Uh, Welcome to our second video for week 3. And today we're going to be introducing the standard normal distribution. So the normal distribution is continuous, building on our last video. It's bell-shaped, like this picture over here on the right. It's used in many different disciplines. A lot of things associated with humans, when you group us all together, tend to form normal distributions, lots of things in nature. You see it in medicine, in health, in business, in economics, in social policy, and psychology. And it's the basis for the inferential statistics that we will learn about during the second half of this course. So everything after week 3 depends on the normal distribution. So super important. It has several different names. So it's called the normal distribution or normal curved. It's also called a bell-shaped distribution or a Gaussian distribution. Gauss was a famous mathematician and physicist, so it was named after him. The normal distribution, that bell-shaped curve, depends on two parameters, two important values. First is the mean. Second is the standard deviation. So the normal distribution depends on the population mean and the population standard deviation. A random variable x that has a normal distribution is written as x is n, and then in parentheses, mu comma sigma. So that says that x follows a normal distribution with mean mu and standard deviation sigma. Of those two parameters, the mean determines where the center or the peak of that normal curve is. It tells us where along the number line the peak of the bell will be. The standard deviation, sigma, determines how wide or narrow that normal curve is. Is it a super skinny bell or is it a low flat bell? The cumulative distribution function is px is less than little x. And we find those probabilities or the normal distribution either by using a table or by using technology. And I'm assuming the most common methods in this class, you're using probably a TI of some sort or GeoGebra. So try not to freak out. I know it looks a little scary, but these are just a collection of normal distributions. So a couple facts about this normal curve. First, we know that it's symmetric about the mean. So the mean mu is where the peak is. So in the picture on the left, all of these curves have their mean at 0. And if we fold that picture in half, we get two perfect mirror images. Also, the mean, median, and mode should be approximately the same because the graph is symmetric and has a nice, clear peak in the middle. This is a unimodal graph, and all of those measures of center should be right on top of each other. Just like any other continuous probability distribution, the total area under that bell shape should be equal to 1. And this is something unique to the normal distribution and a few other curves. That bell-shaped curve approaches, but it never touches the x-axis. So you can see, particularly for the pink and the red curves in this picture on the left, that they flatten out pretty quickly and they get closer and closer to that line at the bottom, but they never touch it. And we can see some of those longer ones, the blue and the light blue, flattening out, but they will never touch the x-axis. Using math terms, we would say that the x-axis is an asymptote for the normal distribution. There's also an infinite number of possible normal curves, one for each unique pair of mean and standard deviation. So this picture shows a whole bunch of different normal curves that have the same mean, but different standard deviations. And there's an infinite number of standard deviations. And then we can take that set of infinite bell curves and shift them left or right, moving their mean. So an infinite number of possible curves. That infinite number of possible curves posed some problems to mathematicians who didn't have access to TI-84s and computers. So the standard normal distribution is a normal distribution of standardized values called z-scores. We've talked about z-scores before. A z-score is measured in units of the standard deviation. So mathematicians started using the standard normal distribution because it was easier to convert a bunch of different x values into z-scores and then use the same normal curve for everything than it was to recalculate everything by hand for each unique normal curve. I'm going to introduce the standard normal and z-scores here, but if you're using a calculator and not the table that I provided on Canvas, you don't need to worry about the standard normal distribution because your calculator can work with any normal distribution. But for those of you who are going to use table E, the mean for the standard normal distribution is 0, and the standard deviation is 1. And the transformation that we've seen before, z is equal to x minus the mean divided by the standard deviation, will convert all of your data values x into z-scores and produce a standard normal curve. Z is a normal distribution with mean 0 and standard deviation 1. The x value comes from a normal distribution with mean mu and standard deviation sigma. So z's, the mean is 0, the standard deviation is 1. For x's, that mean and standard deviation are specific numbers that are not likely 0 and 1. So let's practice some z-scores, talk about what they are, and calculate some. The z-score, z equals x minus mu over sigma, tells you how many standard deviations the value x is above or below the mean. It measures how far we are from the mean in terms of standard deviations. If z is positive, x is to the right of the mean, x is bigger than the mean. If z is negative, x is to the left of the mean, x is smaller. And if z is equal to 0, x is equal to the mean. The z-score allows us to compare data that are scaled differently. So we saw the z-score before when we were comparing data values from different data sets. And we looked at two students who were at different schools using different grading systems. That's what z-scores allow us to do, but they're also used to standardize the normal curve. So let's go ahead and do an example. So suppose x is a random variable that is normally distributed with a mean of 5 and a standard deviation of 6. Find the z-score for x equals 17 and x equals 1. Interpret the z-scores. So let's go ahead and start with x equals 17, and we'll use our z-score formula. Z is equal to x minus mu over sigma. So for x equals 17, we're going to plug our values in. 17 goes in the x spot, our mean of 5 goes in for mu, and our standard deviation of 6 goes in for sigma. Remember that you need to do the subtraction in the numerator before you divide, or you need to type it in your calculator exactly like it's typed on the screen. using parentheses around the numerator. I know 17 minus 5 is 12, and I know 12 divided by 6 is 2. So a raw data value of x equals 17 produces a standard z-score of 2. And what that tells us is that 17 is exactly 2 standard deviations above the mean of 5. Let's try it again for x equals 1. So same idea, we're going to take our z-score formula. X is 1, our mean is 5, our standard deviation is 6. 1 minus 5 is minus 4. And 4 divided by 6 is 2/3, which is about 0.67. So z is negative 0.67. You'll notice this is a decimal answer, and that's okay. You will also notice that we round z-scores to 2 decimal places. And you'll see why that is in another video where we talk about how to read probabilities from table E. So there is a reason to do this. We just haven't seen it yet. So I'm asking you to trust me for a short bit and round your z-scores to 2 places. Looking at this specific z-score, we know that x equals 1 is 0.67 standard deviations below the mean of 5. So one more thing that relates to those z-scores, and then we can move on to our next topic. So if x is a random variable and has a normal distribution with mean, mu, and standard deviation sigma, the empirical rule says the following. It says about 68% of the values lie within 1 standard deviation, 95% of the values lie within 2 standard deviations, and 99.7% of the x values lie within 3 standard deviations of the mean. So let's take a look at what that looks like on that picture. So you can see that this axis has been labeled with the mean in the middle, and then 1 standard deviation below, 2 standard deviations below, and so on. And it says 68% lies within 1 standard deviation. So that's from this point here all the way across. So let's label that. 68% of values are in this region here. So if I were to shade between those 2 lines, there's a 68% chance that a randomly selected person from the sample would fall in that area. Fall between -1 sigma and +1 sigma. For 2 sigmas, we've got 95% of the data. So from here all the way down to here is 95% of our data. When people talk about a normal curve and we talk about the average human or something behaving average, we're typically talking about within 2 standard deviations. That's the bulk of the people. Outside of that, you are more extraordinary, which can be a good thing or a bad thing. There's no value judgment there. It just means it's less common. Between 3 standard deviations is the 99.7%. So all the way down here, which is almost everybody. That only leaves us 0.3% for those 2 tails at the end. This is great because as we learn to calculate probability in a later video this week, knowing the empirical rule is going to allow us to check our work and make sure that the answers we're getting make sense. For example, we know that the whole curve has to add up to 1. So if I've got 68% in the middle, 100 minus 68 is 32. And if I cut 32 in half, that's going to give me 16% this way and 16% this way. That's going to be helpful if I'm trying to estimate probabilities from the normal distribution or check my work. We can do that for the other two values. If 95% is between two standard deviations, that leaves us 5% for the tails. And if I cut 5% in half, that gives me 2.5%. So from here outward, it is 2.5% in each direction. For our last one, we have 0.3 left for the tails. And if we cut that in half, that's going to be 0.15 for the outer tails. So knowing the empirical rule and understanding that normal curves are symmetric can let us check our work moving forward with probability and the normal distribution. This rule is also known as the 68, 95, 99, 7 rule because it tells us that those percentages are within 1, 2, and 3 standard deviations of the mean. All right, if you have any questions about what you saw about the normal distribution in this video, please let me know. Otherwise, I will see you in the next video.